Good afternoon, good morning, good evening, wherever you might be. My name is Pierre Edward Vincent. I'm with SP Brazil, and I'm standing in today for Sergio Cavalcante, who's probably on his way and will join us later. Um, First of all, thank you for joining us today. I'll present a little bit the upcoming events at SP Brazil, and then for this Tech Tuesday of the month of June 2024, we'll have Nigel Leggett present on ultrasonics. So a couple of exciting events. They are well-established events in Brazil. In a few days, there will be the DCOM Brazil Symposium. So if you have not registered for that, you still have a little bit of time. It'll be in a few days, next week, I believe. Then in August, busy summer, about an event every month in the coming period. So August will be the workshop for operational safety, the WSOP. Then you'll have in September the Brazil FPSO symposium, and towards the end of the year later you'll have another workshop on operational safety for offshore wells. So a pretty packed calendar as usual. You'll find all the information on SP Brazil website or the LinkedIn page. So without further ado, I'll introduce Nigel. Nigel and I met in Aberdeen, and I thought the conversation with him was quite interesting. The presentation was really good. The technology was fascinating, and it's a pleasure to welcome Nigel for the Tech Tuesday today. I'm sure you guys will be excited about what he will present. Nigel Leggett has over 40 years in the oil industry, initially working with a major service company and an international oil company with a brief venture into private equity. The bulk of his career has been working with small, innovative technology startups. In 1995, Nigel was a co-founder of Sensa, the first company to introduce fiber optics into wellbore for the purpose of monitoring production and well integrity using distributed fiber optics acoustic and temperature measurements, something which is more widely used today, but was pioneering at the time. Since then, his focus has been on the research and development of new technologies to enhance well integrity surveillance, to improve pre-P&A survey and P&A verification. Sirius Ultrasonics was started in 2018 to further develop advanced ultrasonic systems successfully used in pipeline inspection for downhole inspection applications. Nigel is an active SP member and currently lives in Poole, Dorset. Nigel, the floor is yours.
Thank you very much, Pierre. Thank you very much. And good evening to all listening or wherever you may be. Thank you very much for your attendance and interest in what I'm about to present. So as Pierre said, it's Sirius Ultrasonics. And Sirius Ultrasonics started in 2018. It was initially called Sirius Downhole, but we moved to Sirius Ultrasonics is because that's our unique proposition, ultrasonics. And ultrasonics was a very strong science back in the 60s and 70s when it was used in the defense industry. But since the 80s and 90s, when computers came along, there's been very little work on pure ultrasonics. So we reformed a group of kind of nearly retired engineers who knew a lot about ultrasonics to really take what was developed in the late 80s or 90s and bring it up to today's technologies, which we'll see here today. So everything I'm going to present this evening is around this one simple slickline tool, and it's a slickline memory tool. This technology, as it was spun out from a very successful investment by Shell and Chevron and a Norwegian private equity company to develop what was previously with defense research and kinetic in the UK, which is basically military technologies, to do pipeline inspection, and they developed a unique intelligent pig to inspect pipelines, subsea pipelines first and foremost. And our unique proposition was its ability to do that in gas as well as fluids. So the technology was then spun out at the request of Shell and Chevron to see whether we could use the same technology for tubing inspection. The driver then in 2018 was to lower the cost and improve the efficiency of tubing and casing inspection. So the ability to measure to a high degree of resolution of tubing ID and wall thickness simultaneously, but in a small slickline memory tool. And that was the criteria we were given. So everything we present tonight is around this one tool. There's two versions. I say one tool. We have a small centralizer tool for really 2 7/8 tubing up to 5.5, and then we have a larger centralizer really for 4.5-inch tubing up to 9 5/8. We do have slip-over centralizers to do larger diameter casings if required. So everything's about this tool. It's a 4 meter long, 2 1/8 typical nominal size of the body, 2.75 down here at the centralizer, and the one single rotating transducer at the bottom. And there's a picture of the tool. There's your single rotating ultrasonic transducer. Centralizer, so everything below this centralizer here rotates, the rest is stationary, and up above in this window here, it's not very clear, there is a secondary transducer which strikes against a known datum reference, and it's submerged in the fluid. So we got a true compensation of the reservoir fluids, or the formation fluids, or the fluids we're running the tool in to get an effective speed of sound. So this is the actual hardware I'm going to talk about today. So it's a very simple slickline memory tool, 4 meters long. We typically running with 2 batches, so it's 5 meters long. The principles of its operation, and it's similar to other ultrasonic tools that you're probably familiar with, which are bigger. We have one rotating ultrasonic transducer. This rotates at 3 revs per second, 180 RPM, and emits a pulse 60 times every revolution. So it's the time of flight of that energy hitting the tubing wall or the casing wall, and the return. The time of flight will give us the internal radius. Simultaneously, that energy goes into the casing or the tubing wall and starts to resonate. And we get reflections coming back. That's in the time domain. And in the frequency domain, we get several of these peaks. And it's in the frequency domain we used, the resonant frequency of that tubing and casing will give us the thickness, the absolute thickness of that tubing. I'll go into into kind of the unique proposition of Sirius, because this is typical science of the ultrasonics tools, but the Sirius is unique in the way we actually manipulate our signals. The unique proposition of a Sirius is the high fidelity ultrasonics we've achieved. Over here, this is probably an ideal signal which we would want to emit from a transducer. We would ideally want a broad band, so we're actually working between a 500 kilohertz, typically up to 3 megahertz. We are going higher now, and that will give us a broad band response, allowing us to do high energy. We can resonate casings at the lower frequency, but we have the high frequency to get very clean signals and to get these artifacts which we plan to be able to detect, or we wish to detect in the future when we go to potentially through tubing CBLs. So such a signal, we get a nice square pulse and a very sharp, in the time domain, a sharp acoustic pulse. That's the ideal signal. But in reality, when you apply a reference signal like that, an electrical signal into a transducer, the response is typically in this form. It's a far away from the ideal reference. The distortions, everything, the response, the characteristics of a typical transducer will give you this very erratic response and an effective range, which is a far narrower than what our desired range. And this is because the electromechanics of the transducer, the characteristics of the PZT, etc., all produce a very erratic and fairly narrow band response. In the time domain, this results in a very noisy signal, not a very clean signal. So this is a typical ultrasonic transducer response that you'd use in existing ultrasonics in your industry, whether it's in sonar detection, in ultrasonic medical devices. It's all very similar, very narrow band response coming from a transducer. What we do in Sirius is we manipulate the received signals to produce a response which is very close to the ideal reference which we're looking for. So we manipulate the input and output signals to produce this very square response, and going from relatively low frequency right up to very respectable 3 megahertz. At the moment, we're actually working in labs where we're coming down to about 100 kilohertz and going up to 5 megahertz, which is unique in ultrasonics today. And the result of having high frequency with a very sharp signal like this produces what we call ultra high fidelity acoustics. And that's the unique proposition, one of the unique propositions about Sirius. Everything we do in Sirius is a direct measurement. And none of it's derived. We work with direct measurements. Now, this is just an example of a raw data set. So I'll try and explain what we've got here. I mentioned that we rotate that transducer at 3 revs per second. Every rotation, we do 60 shots. This red line is one of those 60 shots followed over 160 revolutions. So basically 3 revs per second is about 50 seconds of data as we pull out the hole. This is time of flight along the bottom here on the x-axis. And what we get is this is the time of flight of that first pulse hitting the tubing wall or casing wall and coming back. So that's my high intensity first return coming back. And as you can see, as we pull out the hole, we get to that point, which is a joint, and we go into a perforated joint in this upper section here. And as you can see, this joint is slightly later in time, so it's going to be a slightly bigger internal diameter. These are the resonances I spoke about, which are these waves coming back from bouncing backwards and forwards internally within the wall. So the frequency of these reflections will give us a high resolution thickness measurement. The resonant frequency of a tubing or wall is going to be directly proportional to its frequency and thickness. As you can see, as we pull out over a perforated joint, we don't get any of these thickness measurements. And these are the perforations. So that's the clarity of the raw data we work with within Sirius. These are subsequent secondary and tertiary reflections of that same pulse as they come back. So these are going to be mimic reflections of the first, so we ignore these and we just look at this first data set. So as a tool, as an ultrasonic tool, we've got some case studies and just showing it as an alternate solution to the internal inspection of tubing and casing compared with a multi-finger caliper. And our first job was done for Total offshore, and this was a slot recovery. So inspection of a 9.5/8 casing in the upper section, where it was roughly about 65, 67 degrees, where they had already done 3 side tracks, so they were very concerned about rotary wear. So our tool was run below a multi-finger caliper, a 60-finger multi-finger caliper. And this is just a comparison between the multi-finger caliper results here in the bright blue. This color range, because unless your eyesight's fantastic, you can't see it. But this color range here, the full range is about 26, 28 millimeters. Whereas the ultrasonic over this same section, this color palette is about a 4 millimeter range. So you can clearly see we've got this rotary wear. The tool is rotating as we come out. This is very typical of a logging tool as we come out, but we're tracking this wear here. And at this point here, I think we've got maximum wear. So this is looking at the internal radius of the casing at this particular point. So we can track, we're seeing the rotary wear. Coming down into the plot here, we have not only internal radius measurement here, both in the heat map and the analog trace. You see the mean, you see the maximum there. You clearly see there's about, I think in this phase, about 8 millimeters of wear, not 8 millimeters, but 5 millimeters of wear here. And this, on the other hand, is the thickness measurement. And it's this measurement here which was so valuable in this application, because in the past they were using multi-finger caliper. They were applying it to the API calculation for casing wear and burst pressures, and they were getting about a 35, I think, using the multi-finger caliper, about 35 to 37% of wear. And their cutoff was about 30%. Using the ultrasonic tool, we've got an absolute measurement of thickness here in the orange. As you can see, it's very consistent, the red line here, and we can see that we've got the wear here in the blue, which resulted in about 27%. So it saved a well. It's that combination of high resolution thickness and high resolution internal radius is immense value in doing a very comprehensive tubing or casing inspection. Likewise, Total in Italy, where they have tectonic movements, they wanted to identify tubing being pushed by tectonic movement of the casing. And this well, it's 9 5/8 casing, was being pushed. And at this particular point, we could see a distortion of the tubing. Now, this was, to get it in perspective, only 4 millimeters of shift over 20 meters, but it highlights the resolution of our tool. And this was not detected with a multi-finger caliper because of the geometry of where the centralizer is relative to the transducer. Ours is offset by probably about 200 millimeters, which allows you to follow these distortions, where if you've got a multi-finger caliper, these tend to actually centralize on the fingers, and as a result, these type of distortions are very rarely detected. So this is the tool we're running in its basic mode of tubing casing inspection to a very high degree of resolution. The step change in this tool was its ability to become a cement evaluation tool. And it's exactly the same tool as we've been using in there for the tubing and casing inspection. I put this slide up because basically whenever you take a new technology to the oil field, there's always skepticism. And what we're saying about our tool is our tool works in the same manner. It uses the same theory as the existing ultrasonic imaging tools which are run and have been run for the last 30 odd years in the industry. And this is just one extract of showing the principles of the existing tools on the market. You've got one rotating transducer, similar to ours, and that rotating transducer, the performance and the frequency response is matched to the casing thickness, because that casing thickness will resonate at a frequency. The thicker it is, the lower the frequency, and the thinner, the higher the frequency. So we select the frequency response of a transducer to actually fit into the thickness of the casing. This is typically the frequency range these tools are running at, typically 300 to 500 kilohertz. Quite relatively narrow band, and this is the typical response you get from a narrow band. If you remember what I showed you earlier, the wider the bandwidth you can get out of the tool, the higher the frequency you can get, the cleaner the signal. So this is a typical, in the time domain, you find the travel time here of the first reflection. So you get the pulse, the travel time, and you get the first reflection. So what that happens is you actually take a Fourier transform in the frequency domain of that reflection, and you get its resonant frequency. That resonant frequency will allow you to determine the thickness. So at the same time, they look at the reflections. So we're looking at this combined energy level coming off the back reflection. Now the back reflections here, coming off the back, which we use for our thickness measurements, will decay in energy level, which is proportional to the material on the back, because things like water will not absorb the energy as much as things like cement being intact. So if you've got cement at the back of your casing, that cement will pull the energy out of the casing, and the back reflection will be less going back. So if you monitor the decay of these reflections, you can determine what's on the material on the back of the casing. So what they do here is typically in low bandwidth tools is they take a window of these back reflections coming off here, they put it into a Fourier transform and get a resonant frequency, once again the same resonant frequency as we've got from the casing, and we get a combined energy level. And from that they can determine through computations from derivations what the material is on the back of the casing. So that's the principles today of the existing tools. So what I want to show you is the advantages of the series ultrasonics engine technique on that same scenario. So here we have the series transducer working in the same bandwidth as that existing ultrasonic tool. So we get a noisy first reflection coming back here, and we get those reflections, back reflections. We take the Fourier transform, we get the same response, and we get that same dip here, which is the resonant frequency of the casing. We switch our series engine on, we go to this broadband, ultra broadband response, and this is exactly the same scenario with exactly the same transducer. We now get the first reflection coming back. So the time of flight to that very sharp point there will give us a high resolution internal radius. And then we can see, because of the high fidelity of our signal, we can see each individual reflection. If we zoom in on that, we can see the decay. And the decay of those reflections in energy level is directly proportional or directly derived from what is sticking on the back of your casing. So if we've got water or gas, there'd be very low decay. If we've got cement, there'd be a high decay, because the cement will pull the energy out every time you get the energy hitting that back face. And also, when we put into a Fourier transform, we only, in the low bandwidth devices, you only get one of these energies, the resonant frequency of the casing. Because we've got such a broad band, we go up and we capture all the harmonics as well. So as we're working at far higher frequencies, we get the higher resolution thickness measurements. And we can also get high resolution energy levels from this by looking at the combined energy levels. So we sum up the energy level of all these reflections, and we watch those decay as well. So there's a couple of methods we use to quantify the decay, either directly here in the time domain, or we can use the frequency domain. We invariably come up with the same answer. This is actual field data from our tool, and here is one waveform, that first reflection coming back, and here are the back reflections we see, and there's that decay, which is going to be directly related to the material on the back of the casing. So what we have here is a high fidelity direct measurement of the cement or otherwise on the back of your casing. Now, we've successfully used this in a number of applications. I've just shown you some samples which have undergone a hydraulic local expander. This is a technique which was developed with Shell and by Shell to close off microannuli. So it's a hydraulic tool, it's running on wireline, and actually it swages the inner casing out, compressing it in the cement to close off the microannulus. So this is just an example of a 4.5-inch tubing in a 7-inch. These samples, they induced a microfracture. They flowed fluid through this microannulus. They then applied 3 expansions, and you can see here where they reintroduced in brown a good bond, and that was enough to seal. So this is just zooming in on that. We get a good trace of thickness. I'll explain these sharp points here in a minute, but basically we see a reduction in the casing thickness at that point as it's stretched and deformed, and likewise we see an increase in internal radius. And this is the resulting cement evaluation log, and with the increasing of the bond or the well integrity sealing off the tips and the roots of each expansion. Just zooming in on that, you can see the red is the good bond, and what we've got is good bonds at the base of those tips and on the tips. At the slopes, we get erroneous data, and that's what's caused those sharp peaks either side of the data set. And that's because our pulse is not coming back to our tool. Because it is at an angle, it's getting reflected and ricochets off, missing our transducer. So we fail here to get any results, but we can clearly see the seals being produced by this expansion technique. Likewise, this same tool has been run with called the Norsk trials. This is a project in Stavanger, which is backed by numerous operators, looking at the various techniques of cement evaluation specifically and well integrity of cement for P&A operations. So this is just a direct comparison of a well-known existing tool and our tool here, the Sirius tool. This was done 5 years ago, and the casing was pressured up to reduce the microannulus. It was pressured up to 40 bar. Ours was done at atmospheric, so we would typically see less of a bond than we would when it was under pressure. And the other thing, this sample has been repeatedly pressured up and exercised, so we wouldn't typically expect that cement bond to be the same. But there's just 2 samples of a like-for-like match with existing technology. So this was produced within about 20 minutes of getting the data to surface. There's no parameters or factors. There's no post-analysis. This is all a direct measurement. All we simply need is the speed of sound that the fluid was sitting in, and the rest of all the information is obtained from that tool. This is an interesting one. This is a sample where the tool is sitting in a casing with a microannulus. So it's a single point, but we're watching that single point. So it's a single rotation of the tool over time. So this is 3,000 revolutions we've got as the tool sits in a casing which is being the pressure. We're increasing the pressure on the casing. So coming over here, the 3D, you can see the microannulus. We see some good bonding at 0 pressure here. And as we progressively increase the pressure, we can see the bonds getting bigger and coming down to this plot here. As we increase the pressure, we progressively increase the bond index. And this is 0 to 60, 60 to 120. You can see there we're going from a light brown to a brown. And interestingly, there's other areas where actually the bond gets worse. So we do see the blue in some areas as the pressure increases get worse. But as you see, the bond index increasing as we apply pressure. So you just see the sensitivity of our tool on the detection. This is an interesting one, just proving the performance of the tool in a sample where we've got multiple scenarios. We've got actual, so this is drilled holes next to the casing. So it's very similar to hydraulic lines put down the side of the casing. So we've got good bonds. We've got some vertical lines here where they've got their holes drilled. We've got the bad bond. It's not, once again, we're seeing a bad bond. We are seeing some areas. And then we have good bond. Now, this is a good bond. In fact, it had been repeatedly exercised, and probably it's not as good a bond now as it was when it was first produced. And interesting, the free pipe, we're showing some areas. When they drained this sample, they still had some samples of beride in there. So there was some reason for these apparent good bond markings here. The interesting thing here is that this was made up of 4 segments of casing, and 2 of the pieces of casing came from the same original tube. And you can see the sensitivity on the thickness. We've almost fingerprinted the casing thickness. If you can see this one here, this section, and that section, if you invert that top section, rotate it radially, you get a perfect match. And we're talking about that sensitivity, I think, is about just over the millimeter from the blue to the red. It just proves how sensitive this tool is at thickness measurements. Now, most tools today, as I said before, you select a frequency response of your transducer to match your casing. And as I said, the thicker the casing, the lower the frequency. The problem is, at the cutoff, when you get too low a frequency, you're going to get such poor results with because you just haven't got the high frequency component. You just haven't got the resolution required. So typically in ultrasonic tools, you've got a cutoff of about 0.8 of an inch in thickness. And this is where we were asked to look at a thick wall casing and see how good our tool is at being able to carry out a CBL in a thick wall casing, which is extensively used where you've got tectonic movements and salts, for instance. So this is a 10-inch, 26 millimeter thick casing. And this sample, they made for the yard test, and they put various components in which they didn't tell us about. They filled it up with relatively fresh cement and asked us to log it. And this was our response. So we clearly saw we had a fairly fresh cement, but you can clearly see the top of cement here. But more importantly, you can very much see the control lines and the hoses which they had installed in that casing. We have successfully gone through 42 millimeters. So with our technology, the thicker the casing, the better. So that's just proving the point. It's a very versatile tool, and there's no reduction in the resolution the thicker the casing. So as I said, we've been going through 42 millimeters of polypropylene and then through 40 millimeters of steel, and still being able to detect the 2 millimeter tape on the inside of the casing. So that's where we are today. That tool is now commercial. We've got tools operating in North America, Australia, tools going to the Middle East. So that tool is already available today. And where we're going with the future with this technology is the capability of doing a through tubing CBL. So that's the ability for us to actually measure. So there are through tubing CBLs available, but the through tubing component is they can run through tubing and then start measuring once they've gone through the tubing. What we're trying to develop here is a technique of actually being inside tubing and actually doing a CBL on the next casing. So you're allowing you to do a CBL casing assessment without putting a tubing. And once again, it's this Sirius engine I spoke about earlier allows us to do this. So not only do we effectively manipulate the reference signal, so once it's gone through the transducer, it's a perfect signal. We can actually distort the signal and transmit and receive to make components acoustically disappear. So that's the technique. And it's a similar way as a whale manipulates its voice when it talks to its partner. It will actually send a reference signal to its partner will return that signal back, and the original whale will actually say, right, I've sent that signal, I received this signal, so I've now got to distort my voice to compensate for both the attenuation in that acoustic path through the seawater, in attenuation and in phase. And we do something which is very similar. So what we're doing is we manipulate the input signals to correct for all the distortions going on in the transducer, in the water, through a steel plate and back again. So this is the scenario. So here we've got actually a tubing which is thicker. So we've got a transducer below a 20 millimeter thick tubing. We've got a standoff of 100 millimeters, and then we've got a casing, which actually in this scenario is either between 10 and 20. But I'll just show you the pulse. So the transducer emits a signal which hits the plate. So it emits from the surface of the tubing. So we're in contact with the transducer in contact with the tubing. We get this signal, pulse is emitted. It bounces off, and we get the first return, the same as what we've shown you before. We get the first return comes back, and then the back reflections. Those back reflections hit the initial tubing. It comes through the tubing, so we get another combination of back reflections. But if we know what we've sent, we can actually subtract that from what we receive, so we just get the clarity of those back reflections from the top. But it's all to do with how we actually acoustically remove this surface, this first surface, which allows us to achieve this. And this is some examples of a field example of this, where we've got the transducer up against a casing, so it's rotating around, but it's offset, so it's very close to the casing. So as you can see, this is one rotation here. So at this point here, we're very close to the casing, and then we're very far away. And then we're looking at the next casing here. So we get the back reflections from the next casing. So when we look in the time domain, we get these reflections here. We go into our frequency domain, we can see these back reflections, and they're actually reducing at that. So this is just showing you the clarity of the data we get in the field. Invariably, we get better data in a wellbore than we do in our tanks, in our laboratories. But it's already showing that the techniques we've adopted or that we've developed in the tanks are working in the downhole environment. But it does require us to put the transducer within a very close proximity to the first tubing wall. So we're working on this. We hope by kind of the middle of next year, we will be actually releasing for field testing a through tubing CBL. Likewise, this is just showing you the multi-casing detection. This is the same tool as we've shown you before, run in various modes, where once again, this is one rotation of the tool. So you can see we're not actually sitting centrally in this tubing, but we are then starting to detect the outer casings. So this is all the imaging coming from the outer casings. Another example here. And this is a clearer one to see, where we've got a 4.5-inch casing in 9 5/8. where it's more centralized. These are at 60 odd degrees, but we can clearly see the returns coming in from the next casing. So it allows us to do an inspection of the subsequent casing and also give you a position. So quite useful for when you're cutting and pulling casings, etc., knowing the position of your tool, your casings in one another. The other thing is, with all ultrasonics, there is a component of thickness on the cement. And we see it more visibly on our tool because we've got such high resolution measurements of thickness. But you can actually see in this case that there is on the CBL some artifacts of the thickness. And this is, you can see the stripes of the manufacturing of the tool, of the casing, but this typically is a typical thickness plot you'll get from a tubing or casing inspection. And there is some overlying effects coming into the CBL. This happens to all ultrasonics tools. We have got techniques now which we're adding to this tool to reduce that effect. So that's the end of my presentation on ultrasonic or high fidelity ultrasonics.
Thank you, Nigel. Sergio, you joined us, so fantastic. I hope you enjoyed the presentation too, and have some questions for us. So to get us started, Nigel, it's not the first time I see your presentation, so it is very good as usual. So on the current readiness or availability of the tool, I understand as it stands, it's pretty compact, memory mode, run on slickline, so conveyance is easy, and the first step of the service or the information you can deliver is high quality wall thickness and potentially corrosion log, etc. Correct?
That's correct. We aren't a service company. We want to focus at ultrasonics. We want to supply these tools, manufacture and supply these tools to service companies or operators if they elect to run their own tools. First and foremost, it's a very simple tool. So we supply this tool to service companies. We are teaching them how to run this tool in 2 hours through Teams or through video calls such as this. We had them initially come over to our facility in Aberdeen, and it was embarrassing because they came over for a week, and by the first morning lunchtime, they were twiddling their thumbs and looking to go on a whiskey tour of Aberdeen. So we no longer have training courses. We send the tool, they open the box, and we talk them through how to use it. It was our intention right from the start to make this a low-cost tool. It's a slickline memory tool, one operator. You have five commands to load the tool, set the tool to a laptop computer, run the tool, goes through the motions, runs at typically logging speeds 10 meters per minute. The tool comes back to surface. It typically takes about 45 minutes to download the data from the tool onto the laptop. And from there, within 20 minutes, you should have a fully processed report. There's no requirement to do post-analysis. There's nothing to do. There's no correction factors to throw in. The tool is fixed, basically.
Great. Excellent. First of all, sorry I was late. I was driving home, so I had some traffic to deal with, but I was able to listen to most of the presentation, Nigel, and I do appreciate and thank you
Pleasure.
for participating in our event. I have a couple questions. I don't know if I heard right the first part of the presentation, but I understand that technology has been used for evaluating cementation, but it has a potential to be used on corrosion monitoring, also on flow lines. Am I right? Or
you're right. In fact, the original technology was developed by what was Defense Research, which was kinetic, and then that was bought by a company called Halfwave, and they developed intelligent pigs. So Nord Stream gas pipelines were the pipelines they kind of tested their technology on, and they typically use thousands of kilometers of pipelines with this technology. We took the core technology and we were asked to make it smaller and develop it for tubing inspection and casing inspection. So we can actually, the unique proposition is we do provide high resolution internal diameter, internal radius, and very high resolution thickness, because we're working at such high frequencies now. And also we are developing the ability to work in gas. So we can, the current tool works in liquids, water, produced fluids. We will be trying out and field testing a tool where it will actually provide ID wall thickness and CBL in pressured gas above 30 bar. And that we hope to be delivering that at the end of the year. So the unique proposition is the combined high fidelity, high resolution measurements of ID wall thickness and corrosion. And the unique thing we're seeing now is the amount of external corrosion on casing, which typically hasn't been detected before because we're working at such high resolution. So invariably, when you've got cross-flow, you've got lots of failed cement or microanalysis, there is corrosion taking place, and we're seeing it fairly often now.
I see. Thank you. Yeah, I do have another question. I have one more, but if you want to jump in, feel free. Okay. Now, I was looking a little bit into the technology, and as I've heard in your presentation and the material you have on your website, of course, we're talking about new technology, and I've read that you've optimized the transducers, right? And there is also a component of receiving data and evaluating that data. So I was curious about how much of a technology is on the interpretation side, is on the software that does all the interpretation. Did you guys develop any time of optimization procedure for this data that you're reading? How was that? How did you get there?
Well, because it's a direct measurement, there's no real analysis. When it comes to internal radius, it's time of flight. It's a clock. Our tool doesn't need calibrating. So you haven't got to fiddle with all the measurement rings and compensated temperatures. It's a time of flight will give you the internal radius as long as we know the fluid we're sitting in. And there's a secondary transducer, which is hitting against a plate, which have a known distance. So we've got compensation, correction all the time for the fluid time, speed of sound of the fluid we're in. So it's fixed. There's nothing you do. So the signal processing is looking at the peaks. It's not analysis, it's basically peak detection. So it's looking for the return signals and it counts the clock. So basically we store a time which reverts to an internal radius. Likewise, we pick up on those resonances which I showed you. And all our software is doing is actually taking the frequency of those. And once again, frequency, we can actually put that directly into a calculation to actually come up with thickness. There's a very small difference between an L80, for instance, and a super duplex. Okay, it's a harder material, but we're talking about an insignificant amount.
That's what I was going to ask you. If it was a trivial question to inquire about the acoustic impedance of the various steel grades, whether there'd be a difference or not really.
And if someone can give us a speed of sound or sample of the steel, right, we could give it to the nth degree of precision. But typically, if we take the average of a steel, we're getting pretty good within the kind of bounds of the resolution we're quoting. But in theory, we can improve if we've got those figures. So it's not an analysis, it's just signal processing to capture those. Likewise with the cement evaluation, all we're doing is looking at the decay of successive reflections. The amount of decay of successive reflections is proportional to what the material is sucking the energy out. So, for instance, if you've got cement, the decay is roughly about 40%. Each peak will reduce by 40% because that's the reflectivity of a steel cement interface. Likewise, if you've got a steel water interface, you'll lose about 6%. And if you've got gas, you're going to lose about 1%. And that's a basic rule in the fundamentals of a book of you reading about acoustic impedance and materials. The acoustic impedance of material is all to do with the reflectivity of the sonic pulse coming off the interface. So R1, basically, I've forgotten the maths, but it's the actual the contrast between the acoustic impedance of the two materials will give you the reflectivity. If we know the reflectivity, if we know the acoustic impedance of steel, we can go and calculate directly. And because though each reflection is coming back and has gone through the same acoustic channel, we can forget about everything else. So all we're looking at, we're going back to the basic formula of detecting reflectivity, and that's determining that's knowing the acoustic impedance of the two materials. So there's no analysis. So there's nothing. And if we don't like the color, all we can do is play with the color map scale. Sometimes right. We're doing a job in Australia at the moment where we're using very light cements. And very lightweight cement really comes up as kind of a pale yellow rather than what we used to is
right.
a dark brown. Because
this is what I wanted. That's what I wanted to ask. Nigel, is that the acoustic of cement, the acoustic impedance of cement must probably depend on the formulation also and its density, etc.
And the depth it's working at, and sometimes you look at these plots and you go, how do they make that dark brown when the cement is in a shallow well and we know it's a lightweight cement?
Lightweight cement, yeah.
We can play with the color maps, but we can't play around with the absolute number. And there's nothing which goes into our. So we got our guys stand there and go, well, I can't adjust it. All I can do is play with the color scheme.
Okay.
So it's no post processing. You press the button and it spits out the answer, and no one can argue.
But does it give you a superior? Because that will probably remain a bit of a mystery for a while. Our ability to predict the capacity of cement, of any given cement, to provide zonal isolation, effective zonal isolation is another problem. So you might see the cement, it might not necessarily be a good zonal isolation. It might be good quality in most of it, and then have a little channel which ruins the isolation. So your tool would allow, with the coverage, to see that channel better.
Yeah, if you know that you put is a lightweight cement, you should be expecting to see a pill. But as long as you've got continuity, remember, we are getting 60 shots of a CBL measurement, a cement evaluation, which is far higher than a lot of others. So we're getting a very high resolution 360-degree image of your cement bond, which is interesting because cement, there's a difference between an ultrasonic cement bond measurement and a CBL, traditional CBL. A traditional CBL is a sonic tool, whether it's an RBT or just a standard sonic tool. It actually is looking at the ringing. And as we know, you get millivolts. So it's really you hit the tubing at one point with a pulse. 3 feet later, you pick up the signal. If it's free and ringing, you'll get a high level signal coming back. If it's dampened, you'll get a low signal coming back. All you're doing is inferring that amount of ringing to it's being dampened. Now, it could be dampened by barite, it could be dampened by pressure, it could be dampened by all sorts of things. So it's not a direct measurement of cement bond. Now, what the ultrasonic's doing, the ultrasonic is looking at the interface between the steel and whatever's on the back. So it's just looking at that coupling. It's not looking any further. So sometimes you do get conflict between what an ultrasonic will tell you and what an RBT, for instance, will show you, or CBL will show you. Now, our tool does both. We can have it in 2 modes because we're actually looking at the first reflection coming off the front. So the intensity of that first reflection coming off the back, or the energy level, will be a function of it ringing. Then we look at the subsequent back reflections, and that will give us the image of what's sticking on the back. So our tool will give you a standard CBL measurement and an ultrasonic measurement. And for instance, we sometimes see where you've got a top of cement or a bottom of cement. On the ultrasonic, you don't necessarily see that because you still get residual cement left on the outside of the casing from the drilling operation. Whereas on the CBL measurement, you'll clearly see it because it's not much cement there. It's a bit like getting cement stuck to your spade. You've got cement, and an ultrasonic will detect there's cement there, but it won't tell you actually there's only 2-3 millimeters of cement there. So you've really got to look at this, what the measurements are telling you. And the great thing about ultrasonic, it will tell you whether there's gas, whether there's liquid, whether there's cement there. And it doesn't necessarily tell you the whole truth about it being free pipe.
Good.
So
So
that's where your analysts come in.
you did show a picture of a fish tank, and you did talk about whales. So it is good we got that covered about the next generation and
Yeah.
manipulating the signal to acoustically remove the first wall. So
Yeah.
the picture you showed shows a transducer very close to that wall. Is that where you think the tool is heading next, or do you think you'll need to be really close, or can you afford to have that offset? And even if, a second part of that question, once you acoustically remove that first wall,
Yeah.
will you get enough quality signal and the energy needed to give you the interpretation on the second string?
Right, there's a couple of taking those questions. There's two ways of doing it. We can take the transducer and have it standing off as we have got it today. But there's complexity to that because we can do it, but it does depend on us doing two signals. So we send a reference pulse, we get the pulse back, and the pulse we get back from the first tubing, it's a bit like your Bose noise cancelling headphones. The theory of this is we get the return signal, we flip it, invert it, and shift it in time slightly, and then we add it to another pulse. So basically we go into noise cancellation mode. And then we fire it again with the noise cancelling, and that will cancel out all the effects of the tubing acoustically.
Okay.
But it relies on us sending two pulses and the conditions not changing. It can be done, and we've proven it can be done. It's going to take a bit more time. It's a lot more complex. Because of the urgency of our tool going to market, the simplest solution, which we've proven, is to put the transducer against the tubing. So what we make, we make the tubing part of the transducer. And there's no variability. So it's the easiest and most reliable method. So that's the way we're going first. So what we're looking to do is have a pad type tool, so it'd be similar in construction to an RBT, where you've got the bow springs and you've got a transducers pads. So we do that. We probably have 12, or we could, in theory, we could have 2 8s, a 16 pad tool, and we will have those transducers against the face of the tubing. That is the easiest way of doing it. It also allows us to do it in gas, heavy oils, heavy muds, you name it, because basically we were up against the transducer, the surface.
The steel, yeah.
So it's got some operational advantages, but it won't give you the 360 image. It's only going to give you 16. So that's the way we want to go initially, but we haven't lost our ambitions to do it the fancy way with the noise cancelling technique.
Okay.
We can also, the other way, going back to the CBL, and we've proven that, and part and parcel of what we're going to do to advance the CBL measurement is in the time domain, we can look similar to a VDL. So we start looking out in the time domain to the next casing. And we've proven we can actually quantify the microanalysis down to less than 0.1 of a millimeter. And we can then see out to the next fracture or fault or next casing or to the formation. That's all available to us today from those signals I sent you. In the time domain, we can see all sorts of things going out and out towards the next casing. In theory, if we've got the power, we should be able to go through 2 casings. These are all things which are doable down the road. What we're trying to do is get track record and do the low-hanging fruits first.
Okay, and on the, you've mentioned the power, so today you can continue with the memory mode, battery powered, etc., or are you also considering constant power supply to give you more energy?
Yeah, we got a V2 in design, which is going to provide higher temperature. It's going to have a more advanced processor. At the moment, our performance is constrained by the downhole processor. We're maxed out at the amount of data we can put through that tool. So what we're doing, that's the only available processor. So what we're doing is actually moving to a different architecture with more processing power. So we should be able to go, I think, 3 times faster in revs per second and have 200 points. Now, the argument behind that is, well, we're actually producing some very good results today. What it will allow you to do is log faster.
Is log faster, yeah.
That's really the only advantage. But so it's higher temperature, higher processing power with a surface readout function now and surface power. The caveat on that is we have got huge amounts of data and we can't get it up the telemetry. It's a bit like a high density, high resolution camera. The telemetry won't take that type of information. So we will have to store a memory, but we can get, say, 10%, 20% of the data up. So what you'll get is visibility. You can get control and power of the tool, switch it on and off, for instance. And then also you can check that you're getting quality data, but low resolution. So you know the tool's working. Once again, you get to surface, you download it, and you can get the art self within the hour. So that's the option. It's just because there's such a data rate, and also a lot of it we're going for, should we say, the lower cost market. So North American market is this tool was designed to go low cost, lower the cost of tubing inspection. That's where we started, and a lot of those cables aren't up to it on a lot of the winches. And we know that there's a lot of issues today in cables, or the condition of cables in these high resolution or high speed telemetry communications. So it can be done, but we won't get the full high quality data, and we hope to get that out next year. Okay. So there are limitations to these data of information rich tools and telemetry.
Great, Nigel. Thank you very much.
Okay.
Very good. So we've reached the hour. It was a great presentation. So the tool you have available today, it's already been run a few times. It is available. It's on rental. It is memory mode. It's very good for certain applications. It'll be superior to multi-finger caliper by providing the wall thickness, which in many cases is what is necessary. Now I forgot to ask, but does it give you a good indication of ovalization or ovality also of the tubular?
It does, and we very rarely see round pipe. Basically, that's a myth. Circular tubing doesn't exist. It's very oval and typically thinner on one side than the other side. Right. And it's thinner in the middle than the ends. It's always thicker at the ends as well.
Which would be a good potential evolution for measurement of the production casing also in terms of deformation. That's easier than cement evaluation.
It is, and they're down to the thickness measurement. Obviously, the detection of corrosion on the outside as well is being very valuable as well. It's with significantly higher resolution than a magnetic thickness tool, for instance.
Right. But ovality playing such a big role on collapse, for instance, then it becomes relevant in some cases.
Some of the work we're doing in looking at the deformation of casing through tubing as just a precautionary where you got tectonic movements.
Yeah.
The onset of, getting to the point where you can't pull your tubing because you've got such deformation of your casings.
Right.
So just monitoring that. That's doable today.
All right. Sergio, anything else?
No, I'm good. As a reservoir engineer, I'm learning a lot with Nigel and you, Pierre. So thank you very much.
Well, I hope to get a tour down to Brazil soon.
Yeah, well, like I said, like we had conversations before the live discussion, and absolutely, if some clients in Brazil would like to consider an application, get in touch with Nigel and discuss that an application.
Thank you very much.
Very good.
Thank you, Nigel. Thank you very much. Appreciate your time. Yeah, thank you very much for fulfilling my place when I had that issue.
No problem. I went pretty fast. The next Tech Tuesday, if we can, I think will be an exciting info about autonomous subsea inspection and the
Really?
this contactless CP measurement, which is very useful for Brazil as well, without having to send an ROV.
Yeah, I'm excited about that. Thank you very much. So I think, do we have any question from the public? I'm not sure. If we don't, I think we're good for the hour. And again, thank you very much, Nigel. Thank you very much, Pierre. And we'll see you next month, right?
Next
Tuesday. Thank you very much.
Cheers.
Thank you very much.
Cheers. Bye-bye.